Hello and welcome to UILBytes. In this fifth lesson on Boolean identities, we're going to explore the remaining laws that we've not discussed yet. So let's go straight to the examples and we'll talk about each one as we go. When we're talking about XOR, exclusively OR means that one of the two terms has to be true and the other one false in order for the expression to be true. And so the way I've taught my students how to do this is I say write down both terms ANDed together twice, and then on one of the terms put a not, and on the other term put a not over the other one. And this basically says that either A is false and B is true, or A is true and B is false. And that's what exclusively OR means. In this situation, even though you have complex terms, the same idea applies. A, B, C, D, or A, B, C, D, and then you would put a not over this and a not over this. Now this is not in simplest form, and we can go further with breaking De Morgan's laws and going further with that. But we'll explore that process in a later lesson. With XNOR, it's the opposite of this. Both terms have to be the same, and so they're either both true or both false. So again, the same process is used to simplify it. Write down both terms ANDed together twice, and on one of the two resulting terms you put an AND over each part separately and leave the other one alone. Likewise down here, A, B, C, D, or A, B, C, D, and we'll do it over the first bunch here. Okay, so that's how you break up XNOR. Now this is the law of the disappearing opposite, and basically there's no name that I've been able to find for this law, but essentially the way you recognize it is if you see two terms ORed together and in one of the terms exists the opposite of this term, that term can just go away and your result is A or B. Here you can see the opposite of CD in this term. This just disappears. You don't need it. And E or CD. This is kind of a hard one to spot, but once you learn how to spot it, it really will help you in simplifying your expressions. Now let's look at the FOIL method. I'm skipping to the last one first. This is just like you would do as in multiplying two binomials in algebra. First times the first, so you have AC, the outer terms AD, the inner terms B and C, and the two last terms B and D. Hence FOIL, first, outer, inner, last. Now this looks like FOIL, but it's not, because the first term of each one is identical, or it's similar, or it's the same. So this is law number 23, which is the reverse of law number 8. So what happens in this case is you just simply list the first term and then the other two. Now what if you went ahead and decided to FOIL it out? Well, that's fine. So you would end up with A and A and C, A and B, B and C. Now the two A's will melt together, leaving just A, and now you can see that you have absorption, because if you remember the absorption rule, when you see a small term inside of a larger term connected by OR, those just disappear. So you end up with A or B, C. So if you don't remember the reverse of law number 8, that's fine. You can still get there by using FOIL, and then the melt together, the idempotent law, and then finally the absorption law. But if you can learn how to spot that, you can jump straight to here, save yourself a lot of time and effort. Okay, that is all the identity laws that you are required to know about. In the next lesson, we're going to start working some different examples that combine several of these laws and learn how to simplify fairly complex expressions. See you next time.